So with this, we have completed the z-test and t-test under statistical significance tests, where we are working on univariate selection of features. So we want to select the features using statistical significance test concept. So to do that, we have done z-test and t-test. So now we will be moving on to the chi-square test. So the chi-square test is a statistical test used to assess the independence or association between two categorical variables. It involves comparing the observed frequencies in a contingency table to the expected frequencies. The test statistics the test statistic follows a chi-square distribution. So far whatever we have seen was a z-test, which is in between continuous variable and a continuous variable. Then we moved on to the t-test. It can be applicable to the continuous, or your dependent variable is continuous and independent can be binomial, or it can have two groups or two categories. And now when we have your dependent variable also categorical, that is multinomial, and your independent variable also categorical, that's multinomial, in that case we have only chi-square test to handle that problem. So that's what we will be looking into. That is a chi-square distribution. But if you want to understand the chi-square better, so you need to know about one more type of distribution, which is known as multinomial distribution. So multinomial distribution is a probability distribution that describes the probabilities of observing a categorical variable with k possible outcomes. Here k possible outcomes are nothing but the k number of categories in a sequence of n independent trials, where the probability of each outcome remains constant across the trials. So let's take one example so that it would be much easier to process it. So multinomial distribution, the name itself is nomial. Nomial is one type of level of measurement, nomial data. Multinomial distribution. So example, let's suppose we have a categorical variable. So we have the categorical variable, and that categorical variable has total sum a b c d, total a b c d e, and these are the possible outcomes of that categorical variable. These are the k, that's equals to 5 possible outcomes of that categorical variable. In a simplest way, if somebody asks you, some like now which class you're studying, for a kid who school, upper school, they teach only, I'm just giving the example. So it's in upper school. In upper school they have 5th standard to 10th standard. So when somebody asks you which class you're studying, so the class is the variable name, and when somebody asks you which class you're studying, so what all possible outcomes you have? Only 5. What are those? Either you can say 5th or 6th or 7th or 8th or 9th or 10th. So total you will be having 6 possible outcomes. That's it. This is what the example of that. This is what I'm talking about. You will have some five in this example, A, B, C, D, E, five possible outcomes of the categorical categorical variable. So that's what when I say, that's what I mean when I say possible. There are five possible outcomes of the categorical variable. So and we observe this variable n times. Let's we observe this variable n times independently. That's the second condition. So we observe this. We observe this variable n times independently. So the multinomial distribution gives us all the probabilities of observing each possible combination of outcomes across the trials. That's what is our multinomial. So our multinomial distribution gives us the probabilities of observing each possible combination of outcomes across the entrails. So now let's write the probability mass function of the multinomial distribution here. So the probability mass function, that's a PMF of the multinomial distribution. So P of, so X, success, P of X1 is equals to X, and P of X1 is equals to X1, and P of X2 is equals to X2. Now capital X2 and small x2, and so on, depends upon how many categories you have. Xk is equal to small xk. So this is probability of getting x1, probability of getting A category, and probability of getting B category, and probability of getting C category if the experiment was repeated n times. That's what it means. Because that's what getting a certain category is success here. So for that, then n choose x1, x2, x3, and so on xk, and then multiply this with p1, that's the success probability of p1 multiplied by x1, oh sorry, power of x1, and then this one will be repeated till xk, and let me put it here, k and xk. So that's it. This is what is our multinomial distribution mass function. So here x1, capital X2, and capital Xk represent the number of times each of the k outcomes is observed, and n is the total number of trials. So p1, p2, and so on, pk are the probabilities of observing outcomes 1, 2, and so on k respectively, and n choose x1, x2, small x1, small x2, and so on, small xk are the multinomial coefficient. We know that what is n choose x1 and x2. Let me show that here. Yeah, so just look into this formula from here. Parameters n greater than 0, that's a number of trials. So p1, p2, p3, and so on, pk, these are event probabilities. It depends upon how many categories you have in your categorical variable, and then here you have support one. So xi belongs to this, and I belongs to 1 to k. So sigma xi is equals to n. Okay, total number of trials basically. N is total number of trials, and it should be greater than 0. and and then PMF is, as we have discussed earlier, this is what the formula. N factorial, that's n choose x1 x2 and so on xk small x, and then probability of event 1 getting power x1, and probability of event 2 getting power x2 and so on xk. So that's what is our uh, the formula probability function to do that. So the multinomial distribution is a generalization of the multinomial distribution is a generalization of the binomial distribution, which describes the probabilities of observing two possible outcomes, either success or failure in a sequence of an independent trials. So let's take one example so that it would be much clear for us. Let's take dice roll. So dice rolling. This is our example. So let's take the example of rolling a fair six-sided die 10 times. So problem is rolling a dice, rolling a fair six-sided die 10 times. So then n is equals to 10 for us. Now each roll can result in obviously one of the six outcomes. You know that these are the six categories. So what are those? The six outcomes are either one, a two, a three, a four, a five, or six. Just take it as six categories under six variables. So we can model this as a multinomial distribution with the k value. Obviously, how many categories we have? So number of categories is equal to k, and how many we have? Six categories. That's it. So you got the n value, you got the number of categories, and you got the respective categories under that. So now you have to start working on your problem. So let's say we want to calculate the probability of observing the following outcomes, saying mm, just a minute. Yeah, let's say we want to we want to calculate probability of observing the following outcomes. So what are those? Two ones, three twos, and two fours, one five, and finally one six. This is what the combination we want. That's it. Now how will we get it? So now to calculate this probability, we need to determine the probability of each outcome and then apply the multinomial distribution formula. So since the die is fair, the probability of each outcome is 1 divided by 6. So therefore, so probability of P1 is obviously 1 by 6, P2 is obviously 1 by 6, P3 is also obviously 1 by 6, and P4, P5, and then P6 all are 1 divided by 6. Now, using the multinomial distribution formula, you just replace those things. So, what combination we want? X1, how many times we want? X1 we want only 1, and X2 we want how many? 3, and X1 we want 2, and X2 3, and X4 how many we want? 2. Okay, 2 ones, 3 twos, and 1 3. Okay, 1 3 is there. 1 3 1 3. Yeah. So for me, this is 1 and then 2 fours. So x4 is equals to 2, then remaining are 1 each. X6 is equals to 1. That's it. Now you have to just replace these things in our formula. So 10, choose 2 comma 3 comma 1 comma 2 comma 1 comma 1, and multiply this multinomial coefficient with the respective values. So first one, all having the uh, equal amount of mm, sorry equal amount of probability. So I'm going to use the same one. So 1 power, first one is 2. Let me multiply all these things together because all are of same. Yeah, so first one is 2, second one is 3, and the third one is 1, then again 2, then 1 each. 1 each. That's it. There ends the matter, and the value that we will get is that would be the probability. So the value that we get after the calculation is 0.0143. So this is what is the probability that we got for this respective combination. So similarly, you can take up any combination, and it's nothing but you plot all these combinations and you plot all these combinations in a distribution. So how many times each combination comes is nothing but your multinomial distribution. So therefore, the probability of observing twos, threes, 1, 2, 1, 3, 2, 4s, and 1, 5, and 1, 6 in 10 rolls of fair six-sided die is approximately 0.0143. So a multinomial distribution is a generalization of binomial distribution which describes the probability of observing two possible outcomes in a sequence of an independent trials. Here we will describe about the probabilities of observing various combinations of the categories in categorical variables in a sequence of n independent trials. So that's it. So applications of multinomial distribution include modeling the outcome of dice rolls, card games, surveys with multiple choice questions. It's also used in fields such as genetics and ecology to model the distribution of traits or species across different categories.